Okay, this is Pre-Calculus 721, and we're going to be talking about average rate of change today. So, first of all, we have this problem here. So we have time and altitude of a space shuttle. So after how many seconds here is the altitude in feet. So what we want to do is calculate what's called the average rate of time. Average rate of change. So how we get that is what's called the delta A over the delta T. So these variables can change, but the delta is the thing which is consistent. Now delta is a term that you're going to see in physics and math a lot of. It just means the change of, right? You've probably seen it with like when you first did slope and stuff. It was the delta y over delta x, stuff like that. So that's where this comes from. So delta A is our change in altitude over delta T is our change in time. So if we look at these examples here, we're looking at, hey, what's the delta? What's the delta A over delta T for the time period of 3 to 21? So between 3 and 21 seconds, what was the average speed, which is the altitude over the certain time period, right? So to do that, let me hop over to my document camera. I might need to focus this. There we go. Okay, so I know that my change in time, this is desktop focus at all. There we go. Okay, so at 21 seconds, my altitude is 4,533, right? And that changes from at 3 seconds, it's 70 feet. Now I want to divide that by the change in my time, which is going to be from 21 seconds minus 3 seconds. Now the order doesn't matter, right? I could have done 70 minus 4,533 over 3 minus 21, right? In general, I will always say do the second one first because it's in general the larger number, and so then you'll just have positives. If I did it the other way, I would just have a negative over a negative, which becomes positive anyway, so it doesn't actually change the value. It just can save you a little bit of time with not having to worry about those negative signs. So if I do this, if I do 4,533 minus 70, and I divide that by 21 minus 3, I get 247.9 feet per second. And again, I want to keep those same units that I have, which is my altitude is in feet, my time is in seconds, so feet per second. Right? So if I want to jump down, and I could do this for every single one, I'm going to kind of jump down just to kind of so we get the point. If I do from 3 till 12, right? So at 12 seconds, I'm at 1,306 minus 70 over 12 minus 3. So that one would be 1,306 minus 70, and then I divide that by 12 minus 3, and I get 137.3. feet per second. And then if I go down to the very last one that we have there, that was me going from 297 minus 70 over 6 minus 3. So that one would be, once again, 297 minus 70 divided by 6 minus 3, and I get 75.6, or 7 if I round it. What is this kind of telling me, right? Well, as my rocket is going higher, my speed has to be getting faster, right? Because what these are is the average speed over that period of time. So over the the second 3 seconds, for lack of a better term, between second 3 and 6, my average speed is only 75 feet per second, right? But as I do my average speed from 3 seconds till 21 seconds, I'm up to 247 feet per second, right? Which kind of makes sense because my rocket should be getting faster and faster as it's been going longer and longer because those rockets are still going, right? So that's effectively what we're looking at. So what these are is the average rate of change or the average speed over these given intervals, right? So let's hop back over to this. So what I want you guys to try now is take a look at number 69 here. So using what we just did, go ahead and answer A, B, C, and D. And then pause and then come back and we'll go over that here. Okay, so on this one, A, what is the average rate of change of the altitude with respect to time? So that's delta A, my change in altitude, over my delta T, change in time. So from 360 to 650. So if I do that, change over to, there we go. So my 650, my altitude is 4,900, minus at 360, it's 2,900. Okay. Over my change in time was 650 minus 360. So doing that one out, 4900 minus 2900, divide that by 650 minus 360, and we get 6.9, we'll call it. And that is feet per second, or the units which they're using there. Right. So that's my average change in that time period. Then on B, what's the average rate of change of the pressure with respect to time? So that's my P variable here. So my pressure is over there in measured in MB, or that's too small, I can't really see it. Okay. So we're doing that one from time 650 to time 2,750. So at time 2,750, my pressure is 400. And then at time 650, my pressure is 850. Then my time change there is, oh sorry, it's 500. I was looking at the wrong thing. 500 is 2,750 minus, I'm going down to 650. So on that one, if I do 500 minus 850, then divide that by 2750 minus 650, and then my average rate of change is negative 0.16. And that is going to be MB per second. Okay. So that's effectively how we're doing these average rates of change. So once you kind of get the pattern, it's not too bad. It's effectively finding slope, which you've been doing for quite a few years now, right? So let's see, why is the rate in part A positive while the rate in part B is negative? Well, it's positive because as I increase my time, my seconds, my feet are going up, right? Whereas here, as I increase my time, my pressure is going down. So that's effectively what negative and positive slopes are going to do for us here, right? Positive is going to be increase as we get larger x's, and negatives are going to go down as we get larger and larger x's, right? And then D, how is the temperature changing with respect to altitude from time 0 to time 3,600? How can the rate be represented using delta? Okay, so my temperature is, let me pull this back up. There we go. So my temperature is this column here. Right, so how is this changing from time 0 to time 3,600, right? So it starts by going up, and then it starts to go back down. Okay, so that might make you think, well, that's different than all the rest, right? But what we're looking at is the average rate of change, the average change over that entire time period. So what I want is my delta temperature over my delta time. So what I'm going to do there, I'm kind of low on room, but we'll pull it back and try that. So what I want is my delta, I'll use a capital T for temperature, over my delta lowercase t for time. Right? So my temperature change, that is negative 17.9 minus 17.8. So that's my second one minus my first one, over 3,600 minus 0. So if I do that, go to my calculator here. Negative 17.9 minus 17.8. And I want to divide that by 3,600. And I get negative 0.0099. Let's call it negative 0.01. And that is degrees per second. Meaning every second my temperature is going down by 0.01 degrees. Right? So again, that is my average rate of change over that time period. Now keep in mind that that does not mean that every second you were going down by exactly 0.01 degrees. It means the average over that time period is that. Why that's important is because, as we are seeing here, it starts going up and then it starts to go down. So clearly it's not always going down, but the average over from start to end, the average is down, which is why that's a really, really important term for us. It's the average rate of change, not the constant rate of change. Right? All right. With that, we're going to round off by looking at this problem here. So we're not going to do this one fully, but I just want to kind of talk about it in general terms here. So this is a really interesting problem because it really kind of highlights how things work in lottery payments now. They actually can turn so much profit through lotteries. So if the lottery winnings is $1 million, right, they will pay you $50,000 again and again and again over 20 years until they have paid you your $1 million, right? But it only costs the lottery $368,000-ish in order to do that, right? Which seems really, really weird, right? They're paying you $1 million, but it only costs them $368,000. So what they do is they invest that in a fairly high returning investment, and then they just pay you out of that. And then by the time it gets to that 20-year mark, it's paid out its last $50,000 payment. So this is what it is showing here, right? So we invest that. We then pay out the so we then get 12% interest on this a amount here, and then I pay out $50,000. So now I'm only down to $362,000. So I've only lost net $6,000, right? But then I keep on doing that, and since I have less and less in my account earning me that 12% interest, I end up taking a bigger and bigger share of what was there until I get down to the very end where I'm paying out the entire rest of it. So if I took this $44,642, got that 12% in interest on it, and that would give me exactly to that $50,000, and then I'd pay out all of it, and I would zero out the A account there, right? So if you graph this, you'll see that this is not constant, even though you are paying out $50,000 every year, since you're getting that interest. It actually goes up and then down constantly, up and then up a little bit less and then down constantly. So we're actually going down by more and more every single time. So if you graph this, it's actually kind of a almost looks like a upside down exponential curve, right? It kind of starts fairly flat and then goes down fairly steeply towards the end when you pay out those last few A amounts, right? As we are seeing, the average change between these first two is only 6,000, but the average change between these last two is 44,000. So that's a pretty big difference in the actual slope or the actual change in net amount of money in the account. All right, so with that, I want you to read through these, answer those questions to yourself, and then we'll talk about it real briefly here. All right, so so in these problems, we're calculating the average rate of change, right? So we're taking the starting amount, the ending amount, we're subtracting those and saying, hey, over this time period, the average change is this. That is not going to mean it is constant, but that is the average change, right? The delta means change in, so it's the value minus the other value or the difference in those. So why is it important to show all of your work when you're calculating the average rates of change? Is it's really, really easy to get things mixed up, right? If I do 0.1 minus 0.2 on top and then 0.1 minus 0.2 on bottom, I'm going to get very different answers. So always writing down, hey, here's what I'm doing, makes it really easy to kind of make sure you're keeping all of those things straight. All right, with that, here is our homework, 72 through 79, and I'll talk to you guys next time.